So there are three big things we compute about random processes. To review, one is the mean of a random process. You'll do that for a particular t or particular slice of time over all your samples or realizations of the process. Calculate a mean just like we did for probability. Second thing we might want to calculate is the autocorrelation function, which is the expectation of this product of two random variables in your random process. Pick the two arguments, one and T2, double integral. And from the autocorrelation function, you could calculate the mean square values. Not wide set stationary, you just use the same T for both arguments. It is wide set stationary, you just use an argument of 0. And by the way, if we know it's wide set stationary and you see it like this where it just has one argument, then in my course it means it's wide set stationary. If it's not wide set stationary or we don't know if it is yet, we need to keep the arguments as two explicit values of time. If we needed these mean square values and we didn't need the autocorrelation function, we could calculate them directly just by calculating these expectations. X squared here instead of an X. Let me do a couple of examples. Here, X is a random variable and we're given its PDF. The random process, Y, is then a function of both T and that random variable X. So we're asked to find the mean and autocorrelation function of Y, and they ask us, is it stationary? See. The mean of Y, here's the mean of Y, right? And Y equals this thing. So it means the expectation of that thing. Is the expectation? Take this function and put it in with PDF. Here's the PDF. And integrate over all X. In this case, over all X greater than 0. So here is the integral we need to take. I won't go through taking the integral, but here is the setup. And it is 1 over 1 plus t. And right here, what do we know? Not a constant, it's a function of t. So it's not stationary, which means it's not wide set stationary. And it's not ergodic. Well, this says it's not wide set stationary. And because it's not wide set stationary, it's also not stationary, strict set stationary. There we go. Mean is not a constant. Okay, autocorrelation function. Remember, it means this. Y at two different slices of time, so we take this guy at two different t's. That would mean this. We can put it all up in the exponent. And again, we put it in the integrand with the PDF of the random variable for X. Here is the integral we need to take, or this guy. I won't go through that. Here is the autocorrelation function. And again, even if we didn't know this already, if you saw this, this is not a function of just the time difference. You actually need the 2 times explicitly. So this right here says it's not wide set stationary. Therefore, it's not stationary, and therefore it's not ergodic. Let's do another example. Here, the random process X is this function where, let's see, A and phi are just constants or parameters, but omega is a random variable uniformly distributed from 0 to 10. Read all these guys. Mean. Get the mean squared directly, and then compute the autocorrelation function and confirm that the mean square is just the same as the autocorrelation function with at the same slice of time. So let's what it is. What's the expected value of that x? Well, you put this function in with the PDF or the random variable. That PDF is just uniform, 0 to 10. So its magnitude and amplitude is going to be 1/10. And it's just constant from 0 to 10. Here is the integral you need to take. That's not too bad, but here's the answer. And you can see it's a function of time, so it's not wide sense stationary, so it's not strict sense stationary, so it's not ergodic. Now, let's do this guy. I'm not going to go through all this in detail. What is that guy? Well, you put that function in, which is what it was squared. So we have a squared cosine squared. In with the PDF, which is just a constant of height 1. Here's the integral you need to take. I'm not going to go through the rest of it. We required tables, but we came up with this. Now, how about the autocorrelation function? Well, there we take what x is at two different slices of time. So you have this a cosine at t1, a cosine with t2. In with your PDF, which was just a constant of 1/10 from 0 to 10. So here is the integral we need to take. And again, I'm not going to go through the pain of taking that integral, but here is the setup. Once you get to this, it's just take an integral. Just like up here, once you had this setup, it's taking an integral. And it came up, resulted in this fairly ugly thing. But if I put in the same, for both T1 and T2, if I just pick T, the same argument for these two arguments, satisfy yourself if you do that, it turns out to be this, which is what the mean square value was. Remember I said you could calculate this directly if you don't need this guy? You're asked to calculate the autocorrelation function and the mean square value. The easy way to do it is to go ahead and calculate the autocorrelation function. And then from there, you don't want to go through the pain of taking an integral you don't need to. Enough for that video.